Welcome everyone to the Cartesian Cafe. Today, we're very lucky to have Dan Schroeder here with us. Dan is a particle and accelerator physicist and an editor for the American Journal of Physics. Dan received his PhD from Stanford University, where he spent most of his time at the Stanford Linear Accelerator. And he is currently a professor in the Department of Physics and Astronomy at Weber State University. Dan is also the author of two revered physics textbooks, the first with Michael Peskin, called An Introduction to Quantum Field Theory, or simply Peskin and Schroeder for short within the physics community. And the second, An Introduction to Thermal Physics. Dan enjoys teaching physics courses at all levels, from elementary astronomy through quantum mechanics. Welcome, Dan. How are you doing today?
Thank you so much, Tim. I'm doing great, and thanks for having me.
Yeah, no problem. It's quite a rare honor to have a student connect with one of his teachers at some point in his education. In this case, I was your student in some sense because I own both of your textbooks. So I'll just flash them right here for the audience to see. So I have your quantum field theory textbook, which I believe I got at MIT when I was a graduate student. I took quantum field theory under Alan Guth there. And before that, I obtained your thermal physics textbook as a sophomore at Caltech when I took thermodynamics. So it's great to be able to connect with you. It's funny because I didn't realize it was the same Schroeder until I actually reached out to you. I didn't make that connection. So yeah, it's great to be able to, many years later, to look you up and now discuss with you these topics that I learned long ago and hope to continue learning more as we discuss these matters. I thought maybe we'd start out by having you tell us more about yourself, your story and how you became a physicist, and maybe a little bit about how you came to write your books.
Oh, well, the story of the quantum field theory book is kind of easy to tell. I need to explain that I was very much the junior author of that collaboration. But when I was a graduate student at Stanford, I first took quantum field theory from a wonderful teacher named Savas Dimopoulos. Maybe some people have heard of him. And he went nice and slow, and I was able to follow most of it. And then the next year, Michael Peskin was teaching the course, and I knew he would go a lot faster and cover a lot more. So I audited the class, and every once in a while, I would get a little annoyed with him because he'd be talking so fast, he'd forget to say something. The step between, he would go straight from A to C without saying B first. And I'd raise my hand in the back of the room and say, excuse me, but we need to assume this or something like that. And I think he really appreciated those interruptions. And one day we were riding the shuttle van up to the accelerator laboratory together, and he asked me if I'd be interested in helping him turn his lecture notes into a textbook. And we were supposed to finish it in a couple of years, and it ended up taking 8. And by that time, I had gone through 2 temporary jobs and finally landed in a tenure track job here at Weber State. It was a very rewarding process and quite an honor to work with Michael on that. I haven't had much opportunity to think about quantum field theory since 1995 when that book was published. Here I teach only undergraduates. So that's that story. And then the thermal physics was a topic that I was awful at in graduate school. I actually took the statistical mechanics course from Michael. And again, I was lost through a lot of it, but fortunately I didn't need it at all for my PhD thesis. So I got through Stanford without knowing much thermal physics, and then a year of teaching at Pomona College. And then when I got to Grinnell College in a leave replacement position there, they needed someone to teach their senior level thermal physics course. It was taught at the senior level there, probably about the same as the sophomore level at Caltech. And I thought, well, I got to learn it sometime. So I voluntarily agreed to teach that class. And fortunately, I had only 3 students, and they were all very good students. So we sat around a seminar table and kind of taught each other the subject. We worked through together the textbook by Cattell and Cromer, which is a brilliant textbook full of insight, and Cromer has since gotten the Nobel Prize and so on. There's a lot of wisdom in that book. but it's not an easy book for students. And so I kind of learned it as I was teaching it there. And then the next year I got to teach the class again to a larger group. And by that time I decided I wanted to cover things in a different order. And I kind of reordered things and where they made sense to me. And then I came here and to Weber State and taught it 2 more times out of a different textbook by Keith Stowe. And there were some issues with that book for the students as well. And so my 3rd time through here, which was my 5th time through altogether, I started writing up my lecture notes, checking my lecture notes, and handing them out serially. And by the end of that term, I pretty much had a draft of a textbook and kind of stumbled into it. And that's what happens, I think, with a lot of physics textbooks is people teach and get ideas for how to teach a subject and start writing it down and then take it to a publisher. And since I already had one successful book, I was very, very fortunate that publishers took a serious look at this draft. And Addison Wesley published it initially, and it's now with Oxford University Press, and it's been successful beyond my wildest dreams. I thought if 10% of the classes in the US use my book, I'll be very, very fortunate to reach that many, and it's been substantially above that.
Oh, that's
So
great.
I guess I stumbled into the right project at the right time, and I was kind of an opportunist about it. But I'm an amateur when it comes to thermal physics. I've done no research in the subject, and I just kind of wrote down what made sense to me.
Okay, well, it's a very charming book, and we'll get to it soon enough. I just maybe one more question I wanted to ask you. I used to be an academic, and I was very much gunning for the research track. And in academia, there are essentially 2 tracks to basically to do research and to do teaching. Most people do both, but it's sort of a matter of emphasis. It appears that you went for the teaching track, or can you explain your choice or how that ended up happening?
Sure. I attended a very good liberal arts college, Carleton College in Minnesota, where teaching was the main emphasis by far. Not much research was going on there, at least in physics when I was a student, and it's probably changed a little by now, but teaching is still the top priority at places like that. And I had a wonderful time there. I had a very good experience. I had wonderful professors and wonderful classmates, and it was just a very positive experience for me. And so I came out of there into graduate school thinking that might be the career path for me. And then when I got to Stanford and saw what things are like at a big university where, frankly, the people were less friendly and the place was much more competitive, and I was not the strongest student in my class, I kind of that reinforced what I already thought, which was that probably a place like this is not where I want to spend the rest of my life, and that wasn't what I wanted. And so I pretty much was determined, even more strongly after a couple of years there, that I would learn what it was like to do some research. I did some research on accelerator physics, applying quantum electrodynamics to future linear colliders, which are still in the future 30 years later, 33 years later. And that was a wonderful experience. And it was quite an honor to hang out at the Stanford Linear Accelerator Center, which is now called the SLAC Linear Accelerator Laboratory or something. It was a wonderful experience to hang out there for 4 years and go to the talks and the colloquia and absorb what was going on and kind of learn about the research process that way, not partly as a participant, but mostly just by being immersed in the laboratory and what was going on there and talking to my classmates and other researchers. And I think that gave me a lot of perspective on physics. But then I started looking for teaching positions, and I taught for a year at Pomona College, another liberal arts college, and then 2 years at Grinnell College. And then I came here to a department at a public open enrollment regional university, which is a very different type of place from those liberal arts colleges. But my life as a faculty member is actually very similar. We have no graduate programs in the sciences at Weber State. And so I do essentially all teaching and try to find mini research projects for students to get involved with, but publishing is not a consideration with those.
Okay, great. Well, I'm glad things worked out for you.
Well, I guess I want to acknowledge that I appreciate being at a place where you can write a couple of textbooks and publish a few articles in a journal aimed at other college teachers and still get tenure and have a rewarding career. So this is a good place for me. And anyone else who's interested in such a career, look around. There's lots of places where I think teaching is valued, and if you put a good effort into it, you can have a good career.
That's great. And I'm really excited by the fact that now with our conversation, we'll be able to showcase to the world you as a teacher to an audience that maybe you wouldn't normally come across. Well, anyways, why don't we get started? And I wanted to illustrate to our audience some of the charm that I think is unique to your book. So I pasted two snippets from your book. One, which is this cartoon of a magician bringing a rabbit into existence, which is your way of illustrating the concept of enthalpy. And then this passage where you talk about small numbers, large numbers, and very large numbers in a sort of comical definitional way. And the funny thing is, so I'm my PhD is in mathematics, but I took a lot of physics courses, and there's always kind of a funny tension between the two when it comes to rigor. And I think in this case, your book is not rigorous, certainly because it's a physics book, but somehow in physics there's the lack of rigor is in many cases a feature, not a bug. And in this case, there's this level of charm to it. And I thought this passage where you what 10 to the 23 plus 23 is 10 to the 23, because right, you could just sort of absorb. You could just kind of throw away small numbers. So physicists have their heart in the right place.
I don't want to get into a fight between the mathematician's way of doing things and the physicist's way of doing things. I started out as an undergraduate thinking I would probably major in mathematics, and then absolutely fell in love with physics during my freshman year in college. And it was things like relativity and quantum mechanics that really hooked me then. I didn't fall in love with thermal physics until I was teaching it much later. But while I've got the floor here, I need to say that both of these excerpts that you put on the screen are stolen, as are most of my ideas. The idea that the enthalpy of an object is its energy plus the work you need to do to make room for it comes straight from Cattell and Kromer's book. And it's written there, it's been ages since I looked at it, but it's written there in approximately those words. And that was a tremendous insight to me when I was finally ready to read that page of Cattell and Kromer and ready to understand what it was saying. Of course, I immediately took that and used it in the classroom. And then it was just ad-libbing in the classroom, thinking, oh, well, what if I wanted to create some object, And then the cartoon, I asked my friend Karen Thurber, who's an artist, if she could draw me a cartoon wizard and rabbit, and she very kindly did, because I can't draw. So I have to acknowledge Cattell and Kromer and my friend Karen for that excerpt in the book. And then the other one, the small numbers, large numbers, and very large numbers, that comes from one of my undergraduate professors who taught my undergraduate statistical mechanics course, Bruce Thomas. And he's someone I've collaborated with more recently as well, a wonderful teacher. And he made that distinction between large numbers and very large numbers, which I then borrowed in my own teaching.
It's fine to, of course, recycle ideas because, thermodynamics is a very old subject. Of course, we can't reinvent the wheel every generation, right? So that's fine.
But thermodynamics is also often a very abstract subject, and it's traditionally discussed in such an abstract way that I think that somehow there was a need for someone to try to make things a little more vivid and put in a cartoon and be a little bit whimsical about it, I guess.
Sure. I thought I'd maybe planned this discussion really as a more informal dialogue. Usually with my past subjects, I've usually outlined more of a structure, but I think given how amorphous a subject thermodynamics is, it would probably be more natural to kind of let it go where it goes. Let's contrast this with, say, calculus, right? Calculus has a very logical progression that basically everyone sticks to. You learn limits, derivatives, integrals, it builds up. Whereas I feel like thermodynamics, there are concepts that we learned at a very young age: temperature, energy, heat, and well before we took a physics course on them, if we ever did take a physics course on them. And so it's sort of not something that is so cumulative, and it just has all these kind of, it's more of a dialectical learning process. You learn the words, you learn some formalism, you go back and you try to make the two harmonious, and it's this more like an iterative process. So I think maybe that's why I think maybe a kind of a discussion might be more suitable. And the way I wanted to organize this is there are really two questions I want to ask, and I think sort of maybe two of the most important questions. And one is trying to learn thermodynamics, and so let me just write them down. So the first question is, what is temperature? Sort of, if you're going to learn anything from thermodynamics, you kind of should know what the answer to that question is. Yeah. And then the second one is, what is entropy? And I guess that's a more advanced topic, because the word entropy isn't kind of a word, an everyday English word, but nevertheless, it's very fundamental to thermodynamics. And it's one of those words where it's described with a lot of poetry in popular science. Disorder tends to increase. And I'd like to somehow try to maybe resolve some of that possible confusion that might come from such a, kind of coarse or poetic understanding. And so what I really hope for this discussion is to sort of dive deeper and relate temperature to entropy, and maybe work out some examples so we kind of get a feel for what the subject is about. How does that sound, Dan?
Sure. I'm tempted to say, may I answer the second question first?
Oh, yeah, but answer it however you want to answer it.
Also start with the first question. It's just that sure. we're going to have to go to this in order to really answer the first question. We're going to have to answer the second as well.
Great.
So that's just a little warning. So empirically, temperature is what you measure with a thermometer. And I think you talked about people learning about some of these concepts, temperature, energy, heat, at a younger age before you take a formal physics class, maybe in an elementary school or middle school science class or something like that. People learn about temperature. And of course, we hear about temperature in the news and we experience temperature directly. But temperature is what you measure with a thermometer. And that's an important thing to understand, because it's not the same thing as energy. It's not the same thing as what we call heat. And those ideas do get confused with each other. So if in doubt, fall back on the idea that temperature is what you measure with a thermometer. And it's not those other things, even though those other things are related. Those are not what we measure with a thermometer. What we measure with a thermometer is temperature. And when I teach in my classes, I get a beaker of ice water and stick a thermometer in it. And then I get a beaker of hot water and stick a thermometer in it, and talk about how you stick the thermometer in and you wait for the thermometer to come to thermal equilibrium with the beaker of water. And once the reading on the thermometer stabilizes, which takes a little while, which is kind of interesting, you have to wait a little while to get a good reading, then you've measured the temperature of the water. And why does that work? We say that there's energy spontaneously flowing from the boiling water into the mercury in the thermometer. We don't use mercury anymore, do we? I need to revise my book, because we don't use mercury anymore. Or if you stick it in the ice water, there's energy spontaneously flowing from the mercury into the ice water, causing a little of the ice to melt or something, right? So the concept of temperature is founded on this amazing fact of the universe, that when you put two things at different temperatures together and wait a while, they will spontaneously come to the same temperature. And one of them will lose energy and the other one will gain energy. And the one that loses energy is the one we say was at the higher temperature. And the one that gains energy is the one we say is at the lower temperature. So temperature is somehow a measure of the tendency of energy to spontaneously flow out of things. Otherwise, thermometers wouldn't work. Okay, so that's one way of understanding what temperature is, but it raises a more fundamental question. Why does this even happen? Why does energy spontaneously flow out of some things and into others? Okay, and that's going to get us into entropy. But there's a first crack at answering your first question. Temperature is what you measure with a thermometer, but that wouldn't work unless it was a measure of the tendency of objects to spontaneously give up energy.
Can I maybe push back on that definition in the sense
Sure.
that you'll say something like the temperature of the sun is this, or the temperature of the early universe was that, and you might not have a thermometer around with you to measure that. So I don't know if that's like a flippant kind of response, but I just wonder if
it's not flippant, but we can get around those ideas.
Okay.
We can get around those problems. We can eventually learn how hot objects spontaneously give off light with a certain mix of colors, and therefore, by looking at the mix of colors the sun gives off, we can figure out what its temperature is, even without going there and sticking a thermometer into it. But that's more advanced, and to understand why all that happens, you got to get to chapter 7 or something, right? That's not going to be the first section of the first chapter of the book. We're going to learn how that works later on. Of course, it's very familiar to people now who have these, I have one in my closet, these infrared thermometers. You point it at anything you want and it tells you the temperature. It has a temperature readout. You get it at the hardware store. Or an infrared camera, even fancier. If you have the money, you can measure temperatures of things, make images that show temperatures of different things in different places. And that's the same idea as how we measure the temperature of the sun, by looking at the color of the infrared light, or in the case of the sun, visible light that they emit.
Yeah, so I guess, of course, we'll get to this, but there's a concept of temperature, and there are different ways of measuring it. I guess the thermometer is a common way of measuring temperature in ordinary life, but as you pointed out, there are other ways of measuring temperature which aren't thermometer related, at least on the face of it, it sounds like.
I can't disagree with that. And are you trying to start a fight?
No. I just wanted to
define temperature as the thing you measure with a thermometer. And then if you want to state some other interesting things about temperature and talk about some other ways to measure it, okay. But fundamentally, that's what temperature is. Let me give you an example of a bad definition of temperature.
Oh, okay, sure.
When I say it's bad, I'm not trying to start a fight either.
No, me neither. I'm just a curious guy.
In grade schools, high schools, I don't know, various levels of school, wherever they teach about these things, or for that matter, a lot of chemistry classes, and maybe even college physics classes that are aimed at a non-science, people who aren't going to go on and become physicists. We often tell people, gosh, I've seen it in a few textbooks that even are aimed at people who are going to become physicists. We tell people that temperature is a measure of the average kinetic energy of the atoms in an object. I use K for kinetic energy, a bar over it for average. K equals 3/2. So the average kinetic energy per particle is 3/2 Boltzmann's constant times the temperature. So you see, you could turn that around. You could define temperature as 2/3 times the average kinetic energy over Boltzmann's constant. And so the little k is Boltzmann's constant. Some people put a subscript b on it. In my book, I don't, because we use it so much. But all right, so I don't like that definition of temperature because it's too restrictive. It doesn't work for a lot of ordinary objects. In fact, a lot of solid objects. For a lot of solid objects, that's not true. It's a theorem you can prove under certain assumptions for classical systems, for particles that are behaving classically. But as soon as quantum effects come into play, it breaks down. And then what if you want to apply it to a gas of photons, which aren't really particles? What about relativistic systems? Photons are a relativistic system. Or what about magnetic systems where there's only a finite number of states that a particle can have, some magnetic dipole that can point either up or down and maybe there's only two possibilities or three or four or something. For all those systems, those systems don't even have translational kinetic energy. So what are you going to do? My definition that temperature is a measure of the tendency of an object to spontaneously give up energy to other objects is much more general than this formula, which is a version of the Equipartition theorem. This is not the definition of temperature. It's not a definition of anything else either. It's just a fact you can prove for classical systems, that the temperature happens to be directly proportional to the kinetic energy. And in 3 dimensions, the constant of proportionality is 3/2. In 1 dimension, it would be 1/2. The better way to define temperature is qualitatively what I said earlier, that a measure of the tendency of an object to spontaneously give up energy. Now, I haven't made that precise yet. And if you want me to make it precise, I can give you an equation for that too, but it's going to have entropy in it. Okay, so to make that precise, we need to define entropy first.
I've just a question on that. So if you take 2 objects, here's the amazing thing, right? I take 2 objects, temperature 1, temperature 2.
Right.
And it doesn't matter what those 2 things are made of, heat will flow from the hotter object, the one with higher temperature, to the colder object, the one with lower temperature.
If there's a mechanism that allows that, yeah.
Yeah, right. I'm wondering, to what extent do the details matter, in the sense of we've sort of abstracted everything away about in terms of the material composition of the object, their proximity, say. I mean, I guess in practice, you did say one thing, which was you had to wait for a while to measure the temperature, right? So you put your thermometer in the cup of ice, and it doesn't change temperature right away. You have to wait. And then the question is, how long do you have to wait until you know that's the actual temperature? So how do you think about, in terms of, this waiting time, and when you really know that it's the temperature, sort of to further operationalize what you just said?
Usually it'll be an exponential process. You can measure the time constant and then wait a few more time constants, and then it's stabilized.
I see. Okay. And I guess maybe that stabilization time might be different for different materials, but nevertheless, there is some stabilization time.
And it's called the relaxation time. There is a name for it. The
okay.
Relaxation time is how much time some system takes to come to thermal equilibrium if it starts out of thermal equilibrium. And for some systems, the relaxation time is a microsecond, and for others, it's eons, billions of years. The universe is not in thermal equilibrium.
Thanks for that clarification. So why don't we get to entropy then?
Sure. So entropy is a statistical idea. It's a measure of the number of microscopic arrangements there can be within an object or within some system. And that's a kind of a hard idea, but if you think of matter as being made out of atoms or molecules or particles, and that these particles can have different amounts of energy, we can ask, how many arrangements are there for the atoms? And then how many arrangements are there for the energy among the atoms? Different atoms can have different amounts of energy. And for large macroscopic objects, that turns out to be a pretty well-defined question, even though it might seem like it's a little bit ambiguous. Which arrangements are you going to count, and which arrangements are accessible and which ones are inaccessible? But it turns out that for large systems, that hardly ever matters, and you can count to enough precision that the imprecision doesn't matter. You can count accurately enough the number of possible arrangements, and to actually come up with a number, you need to use some quantum physics, because in classical mechanics, you can't actually put an integer number on. You can't. Things aren't discrete. There's no way to discretize things to get an actual number, and that's why I have great admiration for Boltzmann and Gibbs and the other physicists who invented statistical mechanics before we had quantum mechanics and could put a number on the entropy. All they could define was changes in entropy, and you can still do that in classical mechanics. You can talk about changes in entropy. But it kind of takes quantum mechanics or some arbitrary convention, maybe, to come up with an actual number for entropy, which is, again, a measure of how many arrangements are possible. And quantum mechanics gives us a way of actually counting things. And the formulas for entropy always have Planck's constant in them because that's what gives us the dimensional factor to get an actual number out of it. Anyway, if you look in my book or any other book on statistical mechanics, they'll start with examples of coin flipping. And if each particle can only be in two possible states, call them heads or tails, then how many possible ways are there for a system of 20 coins to have 10 heads and 10 tails? And you can count how many different ways there are of doing that. And then if you want an example that's a little bit more like most ordinary matter, you could you can take what we call an Einstein solid, which is a model system that I first learned about from another mentor of mine, Tom Moore of Pomona College. He really emphasized this Einstein solid example in his teaching, and I borrowed that. An Einstein solid is just a collection of harmonic oscillators, but they're quantum harmonic oscillators, so each of them can store an arbitrary number of energy units. But the reason it's simple is because all the energy units are the same size. For a quantum harmonic oscillator, the rungs on the quantum ladder are equally spaced, so each unit of energy has the same size. Count how many units of energy it has above the ground state. So then we can talk about a collection of many harmonic oscillators sharing energy, and how many ways are there for all the energy to be in this side, and how many ways are there for all the energy to be on that side? Well, we can count it because you can just count how many ways there are. Or if you have a given total amount of energy, you can count how many ways there are of it being shared among n harmonic oscillators. And this model of, and this was Einstein's 1907 model of predicting the heat capacity of solids by counting how many ways there are of storing the energy. And real solids aren't all identical harmonic oscillators. They don't all have the same natural frequency. And so Einstein's model is actually not that accurate at low temperatures, and Debye's model was better. But Einstein had the fundamental insight that the reason heat capacities go to zero at low temperature is because of these quantum effects and the counting coming into play. So first, let's understand multiplicity. I'm going to write that word. Okay, and let's give it a symbol. And I like to use a capital Greek letter omega. Other people use other symbols for multiplicity, W. Boltzmann used W, I guess, and Cattell and Cromer used G, which is density of states. So they borrowed it from there. But I like to use capital omega. So that's multiplicity. And that's a dimensionless number. That's how many arrangements are there. That's how many possible, we call them microstates, could the system be in, consistent with what we know about it at the large scale, at the macroscopic level. And so just as a simple example, if we have a system with 3 boxes, okay, and let's say 2 units of energy, so each of those boxes represents a quantum harmonic oscillator or something. You can think of it as an atom or some microscopic way place that a system can store energy. And say we have 2 units of energy to put in it. Okay, how can we distribute them? Well, we could put both units of energy in the first box, and that I'll call 2, 0, 0. Or we could put both units of energy in the second box, 0, 2, 0. Or we could put them both in the third box, 0, 0, 2. Or we could put, let me erase a little bit, okay. We could put 1 unit of energy in the first box and 1 unit of energy in the second, and that's what I'll call 1, 1, 0. Or we could do 1, 0, 1, and I'm running out of space here. So what should we do? I'll write the rest of them over here. 1, 0, 1. Let's see. 1, 1, 0, 1, 0, 1. 0, 1, 1. I'm going to miss some. 0.
Yeah, it's okay. I think we get the idea.
Oh,
Yeah.
I want to get the counting right, though. Okay.
Oh, I see. Okay.
Okay. So we've got the 1, 1, 0, 1, 0, 1, 0, 1. No, maybe that's all. Sorry, that's all of them. Yeah. So there's 6 ways to do this. For some reason, I was thinking there'd be more than 6, but that's a different example. Okay, so there's 6 ways that we can put 2 units of energy in 3 quantum harmonic oscillators. I'm assuming that the units of energy are not distinguishable from each other. One of them isn't red and the other one isn't green. They're just units of energy. I'm assuming that the slots I'm putting them into, the boxes I'm putting them into, are distinguishable from each other. There's atom number 1, atom number 2, and atom number 3. Okay, and they're distinguished by their locations in space or something like that, because this is a very, very tiny example of what we'll eventually call a model of a solid crystal in which the atoms are fixed in particular places. So, okay, so here the multiplicity would be 6. Okay, so that the multiplicity is 6 in this example. There's 6 possible arrangements of 2 units of energy among 3 harmonic oscillators, identical harmonic oscillators. And then we can work our way up to larger systems. And I like to do exercises on a spreadsheet where we work out what the formula is for a certain number of harmonic oscillators and for a certain number of energy units. What's the formula? And it's a nice combinatoric formula. So for an Einstein solid, right, if we have n oscillators, so that was 3 in the example I just gave. And if we have q units of energy, which was 2 in the example I just gave, all right, then omega is q plus n minus 1 choose q, if I recall correctly. All right, so let's go ahead and apply it to the example I just gave. Q is 2, n is 3, minus 1. And if viewers don't know what this symbol means, I'll show you in a second. Right, choose 2. Okay, so what that means, so that's 2 plus 3 is 5 minus 1. That's 4 choose 2. Okay, and so what that means is 4 factorial over 2 factorial times 4 minus 2 factorial, which is also 2 factorial. Okay. All right, so what is that? 4 times 3 times 2 times 1 over 2 times 1 times 2 times 1. All right, cancel that. Okay, so we get 6. So we can also write that as q plus n minus 1 choose n minus 1 like this.
That's right. It's the same answer. Yeah.
Right.
Yeah.
Okay.
Yep.
So once you have that formula, then you can plug in bigger numbers without having to actually count all the microstates. And if you plug in numbers that are on the order of 100 or so, which a spreadsheet program can handle just fine, you get multiplicities that are numbers with 100 digits, or numbers with 50 or 100 or 150 digits, depending on exactly what you do. But I think Excel can go up to 10 to the 300 or something like that. So we're within what common computer software can handle. But it's nice to do exercises with those, and of course there's quite a few of them in the book, to just get a feel for how overwhelmingly huge some multiplicities are compared to others. All right, so if I have 2 Einstein solids and I ask, well, what's the multiplicity for distributing the energy equally between them compared to the multiplicity for all the energy being in one and none of the energy in the other, the ratio of those multiplicities is a number with 30 digits or something like that. Okay. All right, and therefore, if all, and now here comes the fundamental assumption of statistical mechanics. If all accessible microstates are equally likely, if all accessible microstates are equally probable, then the macrostates, the large-scale states that have high multiplicity, will be overwhelmingly more likely than the states that have lower multiplicity, that have much lower multiplicity. Not the ones that have just slightly lower multiplicity, but the ones that have much lower multiplicity. And this gets us into the idea where if you take 2 bricks and put them next to each other, and one of them is at a higher temperature, of course I'm using the word temperature, but if one of them has more than its share of the energy than the other, so the multiplicity is lower than it could be, then energy is going to spontaneously flow from one of the bricks into the other until the combined system has close to the maximum possible multiplicity.
I think right now what we have written, it's not clear, this relationship between what you just said in terms of the most likely macrostate is the one with the most number of multiplicities. Because right now we don't have 2 different systems interacting.
Sure, you're right.
Right. So yeah. Why don't we flesh that out a little bit? Because I don't think that's clear.
So now we have two Einstein solids. Okay, so with Na and Qa and another one, Mb, Qb. So this one has, we can calculate omega for this one, and we can calculate omega for this one. The omega for the combined system is the product. In other words, if the block on the left, if block A has 100 possible microstates it can be in, given how many particles it has and how much energy it has, and block B has 50 microstates that it can be in, given how many particles it has and how much energy it has, then for the combined system, again, keeping the numbers of particles and energy units on each side fixed, the total number of microstates is the product, because for every one of the 100 states that the one on the left could be in, there's 50 states that the one on the right could be in. So we would just multiply those and get 5,000, I guess, for the total number of states for the whole system. Okay, and so we could go through an example of this, but the idea is that if, in a simple example, we might make the n's the same and then vary the q's. And so now let's let energy go back and forth between the two sides. Let's let the two objects exchange energy. Well, whenever a unit of energy goes from A to B, QA goes down by 1 and QB goes up by 1. And if it goes the other way, then QB goes down by 1 and QA goes up by 1. So now we can ask, well, for which values of QA and QB would the multiplicity be the highest, and by how much? And what we find is that there's always a value of QA that maximizes this total multiplicity.
Mm-hmm. Maybe let me just clear. Yeah. So basically, you have a total energy. Oh, oops. Let me.
Right. So total QA plus QB is fixed.
Right. And the point is, this total multiplicity is a function of QA and QB itself, subject to that fixed value, the total energy, right? And the point is, you want to now study this multiplicity function as a function of the QA and QB.
Correct.
Mm-hmm.
Right.
And
what we want to do is, so the assumption is that all the microstates for any way of sharing the energy between the two sides are going to be equally probable. Let's figure out then which value of QA is the most probable, which value of QA maximizes the total.
Right. So I should say maybe
we should determine a value of QB, because that's just the total minus QA.
Yeah. Maybe one thing that's worth clarifying, because this is something that I had to re-clarify myself too when revisiting this. So we talked about microstates and macrostate. We didn't quite clarify what we meant yet. So correct me if I'm wrong, but basically microstate will correspond to the, let's say, the individual kind of distribution of energies that you worked out on the previous slide. Whereas macrostate basically involves these high-level thermodynamic variables like total energy, temperature, and if we talk about it, pressure and volume, right? Those are things that don't involve looking at the particular granularities. They just involve these relatively few in number macroscopic variables. So macrostate basically it's just basically the collection of macroscopic variables, like total energy, for example. Is that right? Did you want to add anything to what I just wrote? Or do you think about it differently?
Let me just take another crack at it to see if this makes sense. A microstate is the state of a system described in microscopic detail, where we specify this atom has this much energy, that atom has that much energy, for instance. And we say where all the atoms are and so on. If it's a gas, then they're allowed to move around. Macrostate is a high-level description, as you said. So we might specify that this brick has this much energy and that brick has that much energy, for instance. So And you might say, well, can't I divide each of the bricks in half and specify that as well? Sure, you can do that. Okay, now we have this half of the brick has this much energy and that half of the brick has that much energy. But you can't, I'm not going to let you divide it all the way down to Avogadro's scale, right? So to the level of individual particles. As long as you only divide things up a little bit, we can be fuzzy about whether the macrostate is, the whole system at once or specifying some parts of it. Specifying the energies or the number of particles or something in various parts of it. Here, I'm going to specify the number of particles and the energy in brick 1 and the number of particles and the energy in brick 2. And I'm saying that once we've specified all those things, that defines a particular macrostate. But now I'm going to consider a whole list of those macrostates with different values of QA and correspondingly different values of QB with the total held fixed. And then we're going to ask which one of those macrostates has the largest multiplicity, has the largest number of microstates, and by what factor. And what we'll find is that some macrostates where the energy is more uniformly distributed in a certain sense turn out to have much higher multiplicities than others. And that leads us into much higher probabilities.
So just to maybe wrap up this discussion a bit, so the macrostate in this particular example is essentially, let's say, QA, right? And it's really, right? I mean, there's two variables, QA and QB, but since their total energy is fixed, that gives us one free variable, and we'll just take it to PQA. So the question, the analysis we're trying to do is, what are the number of microstates, this omega right here, as a function of our macrostate QA as QA varies?
Yep. If you plot that, so omega on the vertical axis and QA on the horizontal axis, okay? For moderately large systems, like 100 particles and 100 energy units, so you get a graph with a very sharp peak. And if you ask way out here on the tails, how small is it compared to up here at the peak? Again, for a system of 100 particles and 100 units of energy or something like that, you find that it's 10 to the 30 times smaller or 10 to the 40 times smaller or something like that. And that's a pretty big number, right? You could, if this system is randomly going from one microstate to another, right? If the energy is just randomly moving around, and so the system is sampling the various microstates, all with equal probability, you could sample it 1 billion times a second for the age of the universe, and I don't think you'd be very likely to find it down there, down on the tails of this distribution. And that's for a system of only 100 particles. What if it has 10 to the 23rd particles? Then this peak is so overwhelmingly sharp, so overwhelmingly high, so overwhelmingly narrow that you can bet your life on the equilibrium configuration of this system being very, very close to that peak, never out in the tails.
Right. And it's worth mentioning that basically the width of this peak, I forget, is it like 1 over n or 1 over square root of n, something like that. But it'll
have a square root in it, and whether it's the square root of q or the square root of n depends on which is bigger. And the relative width of the peak compared to the full scale of the graph is typically 1 over the square root of whichever is smaller, fewer, and very, very roughly.
I see. Okay, so let's just I don't know, O of 1 over square root of, let's say, min of n and QA, let's say. Point is that when you have n, Avogadro's number of particles and QA of the appropriate scale, basically that this width is smaller than any resolution you can probe with, right? And so eventually
the relative width becomes one. So Avogadro's number is about 10 to the 24. The square root of that is 10 to the 12. So the relative width is 1 part in 10 to the 12. So one part in a trillion.
Okay, well, 1 in a trillion. Okay, what's okay? Well, I guess.
Well, if you can measure fluctuations to 1 part in a trillion, you might be able to detect some fluctuations there.
Yeah. Okay.
That's not completely unthinkable that we might be able to measure, but the probability of getting a fluctuation 10 times bigger than that, a 10 to the 11, 1 in 10 to the 11 fluctuation, is overwhelmingly minuscule.
Right. Right.
Okay.
That's right. Because that's basically, I don't know what, 10 standard
That's
deviations,
10 standard
right?
deviations,
Yeah,
right? Right. So
that's
it's
right.
exponentially suppressed, right? Yeah.
That's right. I guess there's several things many different forks in the road we can go
But I
along
still
here.
haven't told you what entropy is.
Yeah. Okay. Sure. Let's get back to that. Yeah.
Entropy is just the natural log of this multiplicity. It's times a conventional constant to put it in conventional units, which is Boltzmann's constant. So where the multiplicity is higher, the entropy is higher. Where the multiplicity is lower, the entropy is lower. And therefore, when you put the two bricks together and wait for a while, assuming that all microstates are equally likely, we're going to end up somewhere very close to that peak. And that's going to be the state of the highest multiplicity, or very near the state of the highest multiplicity, which is also the state of the highest entropy, because all the logarithm does is smooths out the graph. It doesn't change where the maximum is. Okay.
Actually, okay. So actually, how do I say it? So we've talked about entropy in a macroscopic setting, in the sense of when you deal with ordinary everyday systems, they have an Avogadro's number of elements. We are in this large n setting where everything will concentrate on the peak entropy, say. But if you're in a more microscopic setting where you have hundreds, thousands of atoms, right? You're right. Then the statement about entropy always increases or whatnot, there you're in a situation where now the full spectrum of probabilities they're all comparable now. There's not like a delta and everything's negligible. So this notion of
I'm going to push back on you saying they're all comparable. How many particles are we talking about?
100 or 1,000, or they're more comparable than the situation we just drew there.
Fluctuations start to become very noticeable. That still doesn't mean that all macrostates are going to be equally likely.
Oh yeah, they're not equally likely, but they're
the
more
tails of the distribution are still very, very unlikely, even for a system of 100 or 1,000 particles. But what does change is the width of the peak is now 10% of the width of the whole graph, or 5% of the width of the whole graph, or something like that. So the fluctuations start to become very noticeable, even though you're still not going to get all the way into the extreme tail distribution. Right?
Yeah, I was trying to, at some point when we get to the second law of thermodynamics, where people talk about entropy can't decrease or is likely not to decrease. I don't know.
I like to say entropy tends to increase.
Tends to increase. Okay, I think that's also the correct way of saying it as well.
Nicely a little bit fuzzy, right? Yeah.
Yes. Yeah, I was just trying to say that things are much more guaranteed when you have more particles because the fluctuations are less.
In a relative sense, yeah. Okay, so the second law of thermodynamics is that multiplicity tends to increase. You let energy move around, and systems are going to try to find the macrostates with higher multiplicity than the ones they had before, because the multiplicities aren't just a little bit higher, they're a whole lot higher, and that makes them more probable. When we take the logarithm and talk about and restate it in terms of entropy instead, the entropy might only increase what looks like a little bit, but you see a small increase in the logarithm of a quantity can represent a very, very big increase in the quantity you're taking the logarithm of. So taking the logarithm to get the entropy, all right, Boltzmann's equation, S equals Boltzmann's constant times the natural log of the multiplicity. Okay. So that logarithm turns a very large number into a number that's merely large, right? But it also changes that very sharp peak into a nice, broad, smooth curve, okay? But that doesn't change the probabilities. The probability is still you're going to be very, very close to the maximum on that curve. And so if we graph for the same system, QA on the horizontal axis, and now the total entropy on the vertical axis, we're going to get some kind of a broad curve like this. And the top part of the curve is right where the peak of that multiplicity curve was. It just doesn't look very sharply peaked anymore. But it's still overwhelmingly likely that for a moderately large system, that fluctuations aren't going to take you very far from that peak. So entropy tends to, if you start out the system over here in an extreme state, it's going to, let me just get another color. If you start out the system over here in an extreme state, it's going to spontaneously evolve that way toward the peak by the laws of probability. And there, of
Right.
course, if you look closely enough, there's going to be tiny fluctuations, and it's not going to be a monotonic change. But for a moderately large system, you can be very certain to 1 part in a trillion or something like that where it's going to end up.
Yeah, maybe it's worth stating a few things here. So one of the things you said earlier was that one of the fundamental assumptions of statistical mechanics, I forget maybe what the right phrase is, that
Called the
all
fundamental assumption of statistical mechanics.
right,
Yeah.
right. So I'll just write it. So the fundamental assumption of statistical mechanics is that all microstates are equally likely.
All accessible microstates.
Okay, sure. Okay,
We,
yeah.
we put them into 2 categories. We say these are microstates we can't get into at all. Let's not worry
Right.
about those. Let's
Sure.
count up the ones we can. As long as there's a mechanism over the time period we're willing to wait.
Right.
So, the issue of timescales is kind of a tricky one in thermodynamics, and you always have to kind of have in your head, over what time scale am I talking here? You stir cream in your coffee and it mixes in a matter of a few seconds, but the coffee doesn't come to equilibrium with the surrounding room for many minutes or an hour or something like that. So you different states might be accessible over a long time period. There are going to be states that might become accessible that are not accessible over short time periods. And that's kind of slippery.
Yeah, I wanted to bring this up because there's many things one could say about this. I mean, first of all, in some sense, this is both an insight and a simplification in the following sense. If you have an Avogadro's number of particles, right, you can't apply Newtonian mechanics to that system and expect to solve it exactly, right? That's impossible. So what you do is say, in my ignorance of all this motion, I'm just going to maybe, let's say, do the simplest or maybe even the dumbest thing possible, which is to say, well, everything's equally accessible. And that's maybe a function of, in some sense, my ignorance, right? And that's maybe how this principle is. I mean, I don't know if you think about it in a different way, but it's sort of like saying, I don't know what's going on, so let's just say everything's equally accessible.
So in Newtonian mechanics, the number of microstates is literally infinity because positions are continuous variables.
Fair enough. Yeah.
And so that introduces some issues. Of course, I don't necessarily want to say that quantum mechanics is easier than Newtonian mechanics, because we're kind of doing some violence to quantum mechanics here too by only counting the number of, quote, states. And in what we really mean is linearly independent states in quantum mechanics. So we're really counting the dimension of the vector space that the quantum state lives in, right? And so I'm really butchering quantum mechanics here. But at least quantum mechanics gives us a way of thinking of things discretely and counting them, whereas in Newtonian mechanics, the multiplicity is always infinite. And then we have to talk about the measure of some space and whether some infinities are bigger than others by some measure and things. And that's conceptually, I think, harder for students.
One thing you did in your book, for example, when you were dealing with ideal gases, right? You started computing entropy in terms of the volume of phase space they occupy. What you did in that analysis was to essentially discretize it by saying, well, you have Heisenberg's uncertainty principle, and so you can kind of chop up your space into boxes whose size is Planck's constant, because that's the kind of the irreducible small length, and then you can kind of go between volumes and counting. I mean, that's essentially what you did, right? And I should say that in mathematics, the way this manifests itself also is you can think about entropy in terms of a counting problem, log of the number of microstates, but there's also a notion of differential entropy. There's entropy of a measure. And so there's sort of a way of going back between the two, also kind of taking a continuum limit or discretizing things. And those are all kind of related. So
now you're using words that are too big for me, so I'll not comment on that.
Okay. Actually, let me just write it. Okay, I can teach you, you can teach me, but let me just say, there's a notion of if you have a discrete probability distribution. I hope that's okay, right? Just a sequence of numbers that adds to 1. Have you seen this formula? This is an entropy of a probability distribution. So what I mean by that is the sum of the pi's equals 1.
Yeah, that formula appears in a problem in my book, and I've never found any use for it.
Okay, but actually, okay, here's the connection between what we've been doing, because it's all written right here. So we look at all accessible microstates are equally likely. Equally likely means you have the uniform distribution, right?
So that would
So
be a
so
special case, right? Yeah.
yeah, exactly. So in this case, if you have
So you
n
can derive
microstates,
Boltzmann's formula at the top of the screen from the one you just wrote.
yeah, exactly. Because now in this case, then in the uniform case, then that means all the pi's are 1 over n. And then you'll
Right.
see that s is indeed, when you just work that out, is just log of n. Okay. Because then you just have all the terms are equal. So you have a minus log of 1 over n. And that just is log of n. Right? Yeah. So anyways, this is just a way of unpackaging maybe that gobbledygook I said earlier about entropies of measures related to kind of you can discretize things, which is what I just did here. There's this discretized version, because in general, entropy is given by an integral when you have a continuous object, a measure. And then when you go to discrete objects, and then you're in this special case of everything being equally accessible or uniform, then you derive this particular entropy, which is just a special case of a more general notion of entropy. Anyways, I brought this up actually. This is interesting in and of itself, but to relate it back to what we just said about classical mechanics and quantum mechanics, you were worried about continuous versus discrete, and this is just kind of part of that story. In your book, what you did was you chopped up space based on the Heisenberg uncertainty relation, which says that delta x, delta p is lower bounded by h bar. And so you can kind of say, okay, well, let me just take a continuous thing, put boxes of size h bar, and then everything becomes discrete. And then you could kind of
I mean, I imagine the particles in wave packet states for which equality holds in the Heisenberg relation, and then say how wide, if they're this wide in position space, they have to be this wide in momentum space, and then we can just ask how many independent ones are there. What does independent mean? It means it doesn't mostly doesn't overlap. All right, there's a cartoon in the book of that. A bunch of wave packets that are kind of right next to each other. Count them: 1, 2, 3, 4, 5. So if you make them narrower, you'll get more in the same volume. Okay, but if you make them narrower in position space, you got to make them wider in momentum space. Then you get fewer over there. By the way, I've probably gotten more complaints over that section of the book than over any other.
Oh, really? Okay.
And there's other ways to do it. My excuse, I guess, is that in chapter 6, I come back and do it very carefully, counting energy eigenstates. Instead of putting the gas particles into wave packet states, which are not eigenstates of anything, put them into energy eigenstates: a 1 bump wave, a 2 bump wave, a 3 bump wave in a box of a given size, and then the counting is pretty straightforward. But I waited until chapter 6 to do it that way.
Okay. Anyways, this was a fun digression. The reason let me get back to the original point I wanted to make about this fundamental assumption of statistical mechanics.
Okay.
Yeah, because how to say this assumption of all microstates being equally likely, that really is a cornerstone of all these computations and the analysis. And what I wanted to ask you, going back to this thing I said earlier about sort of entropy being described at this very fuzzy heuristic level when people talk about it in normal speak or in popular expositions of science. So you'll hear things like, oh, it's the reason why you can't unscramble an egg is because that would be an entropy decreasing event, right? So let's just try to unpack that when you hear a statement like that. And as I'm thinking about this, I'm not sure. I mean, that's true. It's much harder to unscramble an egg than it is to scramble an egg. We all know what that means intuitively. But in terms of thinking about it in terms of thermodynamics, I kind of hesitate a bit, because the setting of an egg and you stirring it, that's not a setting in which all microstates are equally likely, I would say. I think it seems to me more having to do with there are, I would say, let me take like a silly analogy. Like there's one of you and one of me, but there's a billion people. And that's not a statement about thermodynamics. It's just that there's fewer atoms that are Dan Schroeder and fewer atoms that are Tim Nguyen than there are that are lots of other people. Every time you talk about multiplicity, that doesn't mean thermodynamics is involved, is all I'm trying to say. So for me, I feel like when talking about thermodynamics, you're really in this situation about this fundamental assumption of statistical mechanics. Give me your thoughts. Like specifically this scrambling the egg.
Give me my thought. Okay,
Yeah.
well, I don't know enough about protein molecules to calculate the multiplicity of a scrambled or unscrambled egg. Can we do simpler examples than that?
Okay. Yeah. Or I'm just curious if somebody knows you're a physicist and they ask you, Professor Schroeder, why is it harder or easier to scramble an egg than it is to unscramble an egg? Would you resort to thermodynamics, or would you just say, oh, that's outside my domain of expertise?
No. It's just that there's a lot of steps to relate these very, very simple Einstein solid toy systems to complicated protein molecules. But another issue with scrambling the egg is that you're adding energy to the system during the process, and then as the egg cools off, it loses energy and so on. I'm pretty confident that the multiplicity of the scrambled egg is higher than the multiplicity of the unbroken raw egg. And I would assume that has to do with the denaturing of the protein molecules. There's more ways for them to be stretched out and wiggling around than there are for them to be folded in a very precise way. There's only a smaller number of ways to do that.
Yeah, I guess maybe the point I'm trying to get at is in this particular example that we had with the Einstein solid and two different ones, they're put into contact, and then we make the assumption that all microstates are equally accessible, and then we find that peak and say, we find that entropy increases because we allowed all the microstates to be equally accessible. So first of all, that's I think I described that situation correctly.
It's not just an assumption that comes out of the blue that all microstates are equally accessible. So if we look at a Newtonian system or a quantum system, there's a time reversal symmetry to things, which means that if you go from state X to state Y, that there's also a mechanism to get you back from state Y to state X. I'm talking about microstates now. Mm-hmm. And so the quantum system, and I'm not very good with using the right words here because it's just not something that we discuss a lot at the undergraduate level. But there's something called the principle of detailed balance. Are you familiar with that?
I've heard of it, but you have to remind me.
Yeah, I mean, I'm not sure I can state it correctly, but it just has to do with saying that the rate of going from one state to the other is the same as the rate of going back, or the probability. It's I think of it in terms when we do Monte Carlo simulations. That
I was going to say, yeah, in Markov chains. That's where I've heard it. Yeah, that's right.
Mm-hmm. So if you're writing a simulation of the universe and you want to probabilistically assign calculate the chance of going from microstate X to microstate Y, that your system has to always, if you're modeling any classical system or any quantum system, it has to have the same probability if you're already in state Y of going back to state X. Okay, that's the principle of detailed balance. You have to have the same probability of going either direction. And so, at some fundamental level, I think maybe that's the better way of asking whether it's plausible that all states all microstates would be equally likely. Now you might say, well, okay, I can go from this one to this one, I can go from that one to that one, but maybe there's no way I can get to these over here. Well, then those are inaccessible, right? So, but show me a version, show me a force law in Newtonian mechanics, or show me a Hamiltonian in quantum mechanics that'll take you from one state to another that can also take you back.
Hmm. I see. But I think the way you would say this in mathematical analysis is that if you had a Markov matrix that was symmetric, right? So a matrix of all the transition probabilities. Symmetric is just that detailed balance you just said, and it's irreducible, so you don't have different subcomponents that don't talk to each other. Then basically the only stationary measure, the only stationary distribution you could have is the uniform distribution. I think that's the statement. So there's like a Markov chain.
I have no idea if that's correct.
Okay.
I have no idea.
Okay. Yeah. Okay. I think I'm just translating what you just said into Markov chain language.
Okay, so it sounds like you don't like the fundamental assumption of statistical mechanics. I mean, maybe tomorrow someone will discover a system for which the fundamental assumption is wrong. It's a possibility. It's not something I'm going to prove, but I think it's consistent with our experience.
Yeah. No, it's not that I don't like it. It was kind of what I said earlier. It's both kind of, I don't know how much of it is an insight versus an approximation, but it seems to work well, and that's ultimately what matters. I was just trying to clarify whether, given that you have to make that assumption for this kind of analysis, is it really fair to apply thermodynamic reasoning in all situations where one is tempted to make statements about order, disorder, multiplicity, yada yada, when really, since this assumption is what's needed to drive the analysis, that's what one really should be focusing on more, versus like all these sorts of loose ways in which people talk about order and disorder. That's all I was trying to. The point I was trying to make.
You have to be able to calculate the entropies in order to apply the second law of thermodynamics, which is a statement about entropy. You need to be able to quantify the entropies, otherwise it's not useful. So the second law of thermodynamics says entropy tends to increase, and for a sufficiently large system, you don't need to worry about small probabilistic fluctuations away from that. Okay. But now, if I give you some black box and ask you, what's going to happen, some chunk of matter that you've never seen before, and ask you, how is it going to change in time? You might not know enough about it to calculate the entropy of the state it's currently in, or the entropies of the states that it might evolve into. So you still need to know something about how the system is made up in order to know enough about the possible things that can happen and what their entropies would be in order to know which way it's going to go.
Maybe okay. Let's just maybe one more thought on this, because I think we might just be at an impasse here. But I think here's maybe one way to nail this point. If you were an all-powerful demon, Clausius demons, if I had control over every molecule, I could arrange for all the velocities and positions so that they miraculously move all the way into the corner, which would be a huge entropy decreasing event. And that would be possible in that situation because you violated this all accessible microstates are equally likely, right? Because you're in that setting where you actually know completely what's going to happen, to the point where you can't now access every microstate. It just goes to the microstate that is given by Newtonian determinism, right? So all I was trying to say is, since we're not Laplace's demon, then we resign to, in some sense, a statistical ignorance. We make this assumption about all accessible microstates being equally likely, and that's the setting in which we do thermodynamics.
Right. I mean, in Newtonian mechanics, at least, it's ridiculous to even talk about likelihoods. The system is in whatever state it's in.
That's right.
Tomorrow it'll be in this state, the next day it'll be in that state, next day it'll be in that state. So yeah, I mean, thermodynamics is, I don't disagree with the idea that thermodynamics is largely exploiting our ignorance of that. But remember the very large numbers. Just remember the very large numbers, and yeah.
Actually, that does take me to one question I wanted to ask you which was this point about Newtonian mechanics has this feature of time reversal symmetry.
Right.
Nevertheless, entropy, the second law of thermodynamics is that entropy tends to increase. But if thermodynamics is based on statistical mechanics and therefore Newtonian mechanics, how do you reconcile the two? The fact that Newtonian mechanics is time reversible, whereas the second law suggests sort of an arrow of time where it's the direction in which entropy is increasing.
Well, the universe apparently has started out in a very unlikely state, far from thermal equilibrium. So from there, it's just the probability arguments that I've already made. Now, I don't know why the universe started out over here, okay? But you concede that we're starting out over here, and then it's overwhelmingly likely that we're going to end up here. Or maybe I should just be working on the horizontal axis. We start out over there, and we end up near there.
Okay. So are you saying that the way you would answer it is not so... It's kind of funny. It's almost like you're giving a phenomenological answer, not one of the laws of physics, in the sense that, oh, there's a time asymmetry just because in the past we happen to be in lower entropy. It could have been the case that in the future there'd be lower entropy, but that's just not what happens, right? Because you could have just switched time. The laws of physics are the same, and now future is past and past is future. So Dan and I got stuck on this puzzling question about the arrow of time. So I'll just insert some of my own post-conversation comments here. A short answer to our arrow of time paradox is that the fundamental assumption of statistical mechanics introduces time asymmetry. It assumes that future microstates are all equally accessible, with the past determined and the present as an initial condition. Advanced listeners can think of it this way. Diffusion processes like Brownian motion add independent noise to future increments. This causes the diffusion process to spread out in the future rather than the past. Note that running the diffusion in reverse time causes the increments to instead be correlated and not independent. For listeners interested in learning more about this puzzle and some additional perspectives, they can look up Loschmidt's paradox or take a look at Landau and Lifshitz' Statistical Physics, Section 8. So back, my original 2 questions about what is temperature, what is entropy.
I haven't told you what temperature is yet. What symbol should I use for energy? E? Okay. In
Sure.
my book, I use U, capital U, but
whichever.
Let's use E for energy.
Okay. Okay. So here, the inverse temperature is the rate of change of entropy with respect to energy.
For most types of matter, for most objects, if we just plot the entropy as a function of energy, we get a graph that's increasing and concave down.
Mm.
So what does it mean when the slope of this graph is steep? Okay? Like down at lower energies, it has a steeper slope. Okay? That's an object which, if you give it a little more energy, it'll gain a lot of entropy. Okay? If the slope is steep, then when you give it a little bit of energy, it gains a lot of entropy in the process. Okay? Whereas when the slope is shallow, up here, let's call this E sub A and E sub B. So at E sub A, the slope is steep. It gains a lot of entropy for each unit of energy you add, for each little bit of energy you add. When the slope is shallow, it gains only a little bit of entropy for each bit of energy you add. Okay? So what does that mean? That means that if you have 2 objects, and one of them has a steep slope, and the other has a shallower slope on its entropy versus energy graph, and you let them exchange energy in such a way that the total entropy increases, the one with the steeper slope is going to pull in energy, right? Because its entropy increases more than the other one's entropy decreases. Maybe what we should do is have 2 different objects, right? So one object has this much energy, okay, with the shallower slope, okay, and the other one is over here. So, right. So let's look at that and that, okay, and I should have been more careful with this. So let's let the first one be object A and the second one be object B. Okay. Okay, so now we put these objects in thermal contact so they can exchange energy. Energy is conserved. Any bit of energy that B loses, A has to gain. Any energy that A loses, B has to gain. Okay, and we can ask, okay, well, The second law of thermodynamics says that the total entropy tends to increase. What's going to happen? The one with the steeper slope is going to gain the energy because its entropy goes up more by going a little bit this way. Okay. Meanwhile, that one goes a little bit that way. So A's energy increases a little bit, B's energy decreases a little bit. B loses some entropy in the process, but A has gained even more entropy, and therefore that will happen, right? And going the other way won't happen. So A is the object that we would say is at the lower temperature, and B is the object that we would say is at the higher temperature. Okay, because B is the one that's spontaneously giving up energy to A. Okay,
Right.
and therefore we define temperature as the reciprocal of the slope. Okay, so that's the slope. Okay, if the slope is steep, the temperature is low, and if the slope is shallow, the temperature is high.
Yeah,
So
I think it's
that's how that works.
yeah, this is a very nice visualization. So let me just rephrase that just to have a different way of parsing what you just said. So these two objects, they're at their own energies, E sub A and E sub B, and they're therefore at their own temperatures, T sub A and T sub B. And by the definition you just gave, T sub B is higher than T sub A because its slope is lower and temperature is the reciprocal slope, right? So what we just illustrated here, right? So this has higher slope, therefore lower temperature, and this has lower slope and therefore higher temperature. And then sort of the picture you should have in mind is that you can gain more entropy by moving energy to the right. Let me draw. So here, energy EA is going to increase and energy EB is going to decrease because the amount of entropy you lose when B moves to the left is more than compensated by the entropy increased by A moving to the right, precisely because of this slope disparity. And then the equilibrium temperature they're going to reach, it will be the point at which these two slopes are equal, which is precisely them being at the same temperature. And the reason why the slopes are equal is because then there's no net gain by adjusting the energies, right? And that's precisely right.
Yeah, so you've taken it one step farther and asked where does the process end? And the answer is exactly where the two slopes are equal when the objects are at what we would call the same temperature when the slopes are the same.
Yep. Yeah, this is
and that's what temperature is, and that's what this formula is telling us, that temperature is the reciprocal of the slope of an object's entropy versus energy graph. And therefore it is a measure of the tendency of an object to spontaneously give up energy to other objects. The higher the temperature, the more the object will spontaneously give up energy to other things with lower temperature.
Yeah, and this basically is the formal definition of temperature, correct?
Yeah, it's the only definition of temperature.
Okay. Yeah, sure.
I mean, so there's an operational definition.
Sure.
What we measure with a thermometer.
Yeah. Right.
I'm not sure what you mean. What did you mean by the word formal? Is there an informal definition?
Oh yeah, by formal, like in terms of a mathematical definition, which is what this is. Yeah.
I was just wondering if you had some other informal definition in mind.
No, I mean, I mean, there was a potential formal definition in terms of average kinetic energy, because that is.
No.
Yeah, but it's not. It's not. Yeah. Yeah. Okay.
Don't try to define it that way.
Yeah. So this is very nice as a mathematical definition. Now, one thing I'm genuinely curious about, you did mention that the founding fathers of thermodynamics, they had to sort of do things the hard way in terms of not having quantum mechanics at their disposal. Now, I think historically, maybe you can comment on this, because there's Carnot, there's engines, and they thought about reversible, irreversible processes, and sort of the way it's often written is let's say dE, just to be consistent with your notation, and I'm thinking of it as heat energy, so I'll write it as dQ.
No, I'm not going to let you do that.
Oh, so,
what does Q stand for?
Well, at least in your book, it represents the heat, right?
Heat is energy in transit.
Mhm.
So when I talk about energy spontaneously flowing from one object to another, that's what we call heat. It's the energy transferred due to that spontaneous process. So it's
Mhm.
energy in transit, or an amount of energy that moves from one place to another spontaneously and driven by this entropy increase, overall entropy increase. Okay. What I don't like is the little d that you put in front of q. All right.
Oh, sorry. I should have just written Q. Maybe is that what you were complaining about?
Please. Okay.
Okay. Sorry. Yeah, I
I
see.
mean,
Sorry. Okay.
if it's an infinitesimal all right. Yeah. So
Okay.
when you put a d in front of it, people want to say the change in q.
Okay. Sorry. I
And
just
q is not a state function that can change.
got it. Sorry.
It's an amount of heat that flows.
Got it. Fair enough. Fair enough. Okay. Yeah. Okay. All right. Thank you. Thank you. And then Q. Let's see if is TDS. All right. Okay. So I think this is the way people historically thought about the relationship between these quantities, and I'm curious to know a little bit more about the history and how, like, people. I mean, we have the benefit of generations of work. We could just write down these formulas and talk about it as if everything's obvious, but somebody had to figure this out, right? So how did they sort of think about this? Or I don't know if you have any further comments.
I don't know. I'm not a historian, and I've never studied the history. I've read a little bit of Carnot in translation, and maybe a little bit of Clausius and a little bit of Boltzmann, but not enough to have any insight into the history. And of course, history is incredibly complex when you get into it, because they don't have the benefit of hindsight on these ideas, and they're wrestling with them, and often aren't expressing things the simplest way that they could. So I'm not in a position to say that. In textbooks, we always give a little bit of pseudo history, and I do too, and talk about how Carnot came first, and then Clausius, and then Boltzmann. So I know a little bit about the chronology, and who, roughly what was known at one time and by a certain person, and what was known at another time by another person, even if they wouldn't have said it the same way we do. So with all those caveats, what do you want to ask me?
Oh, I just wanted to see if there was a way of, because I certainly, as a mathematician, I'm very happy with the story. I was just wondering if there was any insight to be gained about how people thought about it in such a way that it might give insight into how this was discovered.
Well, everyone's seen that when you put two things at different temperatures together, the hot one cools off and the cold one warms up. I guess people like Carnot and Clausius thought very deeply about that. Now, Carnot did not, my understanding is that Carnot did not know that heat was a form of energy. And he didn't quite distinguish between entropy and heat. And yet he had this deep insight that led him to formulate a version of the second law of thermodynamics and put limits on how efficient engines can be and things like that from that. And by Clausius's time, a few decades later, it was understood that heat is a form of energy, or a means of transferring energy. Even then, it wasn't. So Clausius figured out that there has to be this thing that he called entropy. There has to be this quantity. Every object has a certain amount of it, and it's related to temperature by this formula that you wrote and I wrote. It's the same formula, right? Your formula is the same as mine. Okay. So you just like D's and I like deltas. Okay.
Gosh. Okay.
Okay. So, but it's the same, and you don't need Q, right? You could say just change in energy is T times ds. I call that formula the definition of temperature. That formula embodies the most fundamental thing about temperature, which is that it's a measure of how generous an object is with its energy, giving it up to other objects. Okay. And then it was Boltzmann who made the connection to statistics and microstates, and understanding what entropy actually is in a statistical sense.
Have we answered everything? Is there anything else you wanted to
Well, there's a
say?
lot of things we have not answered, and
Okay.
right.
Okay.
But I hope I've given a basic textbook explanation of what entropy is, how it relates to temperature, and what the second law of thermodynamics says.
Do you have any final, I don't know, any final thoughts about the subject? I know, of course, thermodynamics is a richer subject that can be covered in a single conversation, much less even a single textbook. Yeah, just any I don't know, final thoughts on the subject, or words of advice on maybe people trying to learn the subject?
Oh, those are two different questions. Let me give another thought. We've been speaking very abstractly and talking about some pretty abstract model systems and things. Thermodynamics is also extremely important in the real world, and some people might be less interested in that, and some people might be more interested in that. But I think everyone has a reason to care about thermodynamics. Thermodynamics does, as Carnot showed, put limits on the efficiencies of engines. It tells us that we can make heat pumps that are more efficient than an electric space heater. It's an incredibly important thing to understand thermodynamics to if we care about energy and the climate implications of energy and the energy transition as people try to use more energy more efficiently and get it from better sources. Thermodynamics is what tells us where all the energy ends up. It all ends up as dispersed waste heat that we can't make any use of. And what it means to use energy, right? We can't destroy energy, no, but using energy means taking it from a low entropy form and turning it into a high entropy form where it's very widely distributed. So I guess I think it's important that people understand thermodynamics if they want to participate in making the world a better place through coming up with better energy technologies. And I think I see a lot of misconceptions about thermodynamics, and I guess I would encourage people to get away from those. One of them is that temperature is merely a measure of the average kinetic energy of the system. But another one, a much more specialized one, is that when an engine doesn't achieve the maximum efficiency that the second law of thermodynamics allows, I see in a lot of textbooks and a lot of people talk as if the reason is because, well, there's just friction. And if there were no friction, maybe it would achieve the Carnot efficiency. No, that's not the reason. And it's much has to do with the reason why the heat flows in the first place and how a heat engine works. So I think that there are very, very practical reasons to understand basic thermodynamics. All right, now you also asked if I have some advice for students learning thermodynamics. Don't just watch videos. Get out the pencil and paper and do some hard work and wrestle with things.
Oh, absolutely. Yeah.
That's my advice.
Yeah. I mean, make no mistake, the videos I produce are not a substitute for the labor that is involved in any learning process, really. Not particularly in science and math, but in any field, there's a long pipeline and repetition of doing problems and thinking about it until you really understand the material.
Right.
Great. Well, thank you so much for your time, Dan. This was a very, I think, enlightening to get your thoughts. Certainly, it's rare to hear it from the author himself when learning a subject.
Well, thank you very much for your interest, Tim, and thanks to all those out there who are watching this.